Good morning, students. So after knowing about relative density, here we will know how to calculate the relative density by using the Archimedes principle. So this is from the chapter 5b of class 9 physics. Okay, so first we will know about the Archimedes principle. Okay, the basic idea of Archimedes principle. See the picture first and try to understand. Here this one is the body. Okay, the spherical body is dropped in this liquid. This is water. Okay, and here when it is dropped in the liquid, some water is flow out through this pipe, through this exit pipe, and this water is stored here on this. Okay, so the volume of the spherical body is equal to whatever the volume enters to the water is equal to the volume of the water displaced to the smaller vessel. That means whatever the volume of water is displaced to the smaller vessel is are equal. It is equal. That means whatever the volume is present here is equal to the volume of this spherical body. And now see the weight of the body is taken W1. Okay, when it is outside. So this one, whenever the body is here, its weight is W1, and when it is get inside, you all know that whenever any object get inside the water, then it loses some of its weight. Okay, and now its new weight inside water become W2 as we have taken here. Okay, so why the loss of weight, why there is a loss of weight? So because there is some upthrust. Okay, the upthrust, that is the force exerted by the water on the object against the weight of the object. So that means this one is the weight, W1 is the weight, okay, when the object is outside, and W2 is the weight when it is get inside. So W2 is the weight. Okay, and this one is the initial weight W1 is subtracted with the upthrust. That means whatever the force applied by the water, okay, it is subtracted from the original weight W1, then we will get W2, okay, which is the weight inside the water. Okay, so this upthrust is nothing but the loss in weight. Okay, this W2 is less and this W1 is greater as compared to W2. Okay, this W1 is the actual weight outside the water. Okay, and this W2 is the weight when the object is inside and the upthrust is acting on the object. So by the Archimedes principle, okay, according to the Archimedes principle, this upthrust, that means whatever the force applied by the water on the object, on the body, this one is the upthrust. Okay, and this one is equal to the weight of water displaced. Okay, that means whatever the weight of the water that is displaced, okay, and the water is displaced is equal in volume, okay, na, equal to the volume of this surface, this spherical object. Okay, so that volume of water is displaced, and the weight of this water, is equal to the upthrust that applied on the body by the water. Okay, this is by the Archimedes principle. Okay, by the Archimedes principle, according to the Archimedes principle, this upthrust force acted by the water on the body is equal to the weight of the water that is displaced by the body. Okay, the weight of that much of water which displaced by the body when it is get enter. Okay, so now see the next how to calculate the relative density here. Okay, see the relative density, you all know that relative density is the ratio of the densities of the substance and the density of water at 4 degrees Celsius. Okay, and the another definition of relative density is it is the ratio of mass of a body to the mass of water at 4 degrees Celsius when both are taken in equal volume. And here in the previous example, this one is the volume of the body, and whatever the volume of this spherical body is same as the water present here, and the water that is displaced out. Okay, na. So the relative density equal to mass of the body, okay, and it is divided by the mass of water that is displaced. Okay, the mass of the body that is which is to be taken inside water, okay, and the mass of the water that is displaced. Okay, and you all know that from the second law of motion, that mass into acceleration becomes the force, that is the weight. Okay, so here we have mass of the body into the acceleration due to gravity, so mg, okay, it is equal to weight. So weight of the body in air and it is the mass of the water into gravity, it is equal to weight of the water. Okay, so it is weight of the body divided by weight of water. Okay, but you know that the weight of the body in air that we have taken here as W1, remember this one. Okay, and the weight of water that is displaced out is the upthrust force, is equal to the upthrust force. From this line you can see, okay, the upthrust is equal to weight of the body weight of the water displaced. So we will write in as the relative density equal to weight of the body divided by weight of water. So in the place of weight of the body we will take W1 is equal to divided by upthrust. Okay, but here the upthrust is equal to what? See here we know that W2 upthrust is the loss in weight. Okay, see this here, W2 is equal to W1 minus U. Okay, that is U means upthrust. So upthrust is equal to W1 minus W2, that is the loss in weight. Okay, so this relative density is equal to W1, which is the actual weight, divided by the loss in weight, W1 minus W2. So this one is the final expression. Relative density equal to W1, that is the actual weight outside water, divided by the loss in weight, that is the difference in actual weight divided by the weight minus the weight when the object is inside water. That means the loss in weight. Okay, now whenever the body is taken inside water, there is some loss in weight, and this loss in weight is divided with the actual weight, and this will give the relative density of the body. So how we can calculate the relative density? Now see this picture. Okay, here relative density of a solid insoluble in water. So we can use the direct formula here. Relative density equal to the actual weight divided by the loss in weight. Okay, this one is the loss in weight. Okay, W1 minus W2. So we are taking, see here we have the spring balance. Okay, it will give the weight. So first the solid is weighted, and we have the value W1. Suppose we have value W1, and then the solid is taken inside water. Okay, it is completely merged inside water. Okay, and here the weight is found W2. Okay, this W2 is less because whenever the body goes inside water, some loss in weight, so this W2 is less, and the loss is the loss to get the loss, that means it will W1 minus W2. Okay, so this gives the upthrust, the loss in weight. So in this way we can easily calculate. We have the spring balance, we have the value of W2, we have the value of W1. Okay, so we can easily calculate the relative density. Now see the next point, how to calculate the relative density of a solid soluble in water. Okay, solid which is soluble in water. So see the first line, for the same volume, that means volume of liquid displaced is equal to the volume of solid. As because here we are taking another liquid which is another liquid of known relative density. Okay, here we are taking the liquid of known relative density, and it is the liquid where this solid is insoluble. Okay, the solid which is soluble in water, so we can't take the solid inside water, but we can take another liquid of known relative density, and the solid will not dissolve in this liquid. Okay, that is this solid is insoluble here in this liquid. So here for the same volume, that means the volume of this solid is equal to the volume of the liquid displaced. Okay, that means whenever the solid is taken inside, some volume of the liquid is displaced, and that volume is equal to the volume of solid. Okay, so we are taking the same volume, equal volume. So the relative density is equal to weight of the solid divided by weight of water that is displaced. Okay, with the same volume, solid has the same volume as the water displaced. Okay, now here we have multiplied here with this weight of liquid. See here water is displaced, I have given. Okay, I have written water is displaced, but actually the solid cannot be taken inside water, so that's why we have multiplied here in the relation only. We have multiplied with water weight of liquid. Okay, the same volume of the same volume. Okay, and it is divided also with the weight of liquid. And here mathematically you can easily understand. Okay, now here see here W1, this one weight of the solid is W1 as it is weighted here, okay na, it is, and so W1 is the weight of solid, and here the weight of the liquid displaced, that is here you can see this part is taken here, okay, and this is present here, okay, this is, and this one is taken here. Now we have this liquid, weight of the liquid divided by weight of the water, this one is weight of the water, okay. So if those two are divided, so we will get, you know, the relative density is equal to weight of a substance divided by weight of water. So weight of the liquid divided by weight of water gives the relative density of that liquid, and we know that the relative density of the liquid is given here, okay, it is given. Initially whatever the liquid we have taken, the relative density is known, is a known term here. So we have the value of this ratio, okay, weight of the liquid divided by weight of the water, which is actually the relative density of the liquid, and it is given, okay, this part is given, this one is given. So here you can see this W1 is the weight, actual weight, and it is divided with the upthrust, okay, that means upthrust by the liquid, that is the weight of the liquid displaced, and whatever the weight of the liquid displaced is same as the upthrust applied by the liquid on the object, okay, by the Archimedes principle, okay, according to the Archimedes principle. So here the upthrust means the loss in weight, and we have the original weight, and whenever the object is taken, the solid is taken inside the liquid, we have the weight, okay, after some loss in weight. So the loss in weight is obtained by subtracting those two values, so W1 minus W2. See, this one is the final formula. So relative density is equal to W1, you can see here it is W1 divided by the loss in weight W1 minus W2 into the relative density of the liquid, which is a non-term. So this one is the final formula. By using this formula we can easily calculate the value, the relative density, as because W1 and W2 is given and the relative density is also a known term here. Now see the next page. So here the relative density is to be determined of a liquid. The relative density of a liquid is to be determined, and this liquid is other than water, because for water we know that relative density is 1. So now see, first here W1 minus W2 is the upthrust by water, that means the loss in weight, okay, the upthrust means the loss in weight, which is equal to the water displaced whenever something is taken inside water, okay. Suppose a body is taken inside water, we are considering here liquid, okay, I agree, but we are considering that if any object is taken inside water, then the upthrust by the water is equal to the weight of the water that is displaced, okay. And see here W1 minus W3, W3, here you can see this one is W3, okay. So W3 means what? We are taking W1 as the actual weight of the solid, W2 is the weight, okay, when the solid is taken inside water at 4 degrees Celsius, and W3 is the another weight when the object is taken, when the solid is taken inside a liquid, okay, a liquid for which we have to calculate the relative density. That means this liquid is given, okay, and for this liquid we have to calculate the relative density, okay. So here see W1 minus W3, here this one is W3, that means whatever the weight when the solid is taken inside here, okay. So this W1 by W3, W1 is the actual weight, so this will give the loss in weight when the object is taken inside the liquid. So this loss in weight is equal to the upthrust by the liquid, and this upthrust by liquid by the Archimedes principle, this will equal to the weight of the liquid displaced when the solid is taken. And you know that whenever the solid is taken, the equal volume, whatever the volume solid has, the equal volume of liquid is displaced out, clear. So we know that the weight of the liquid is displaced is same as the loss is the upthrust by the liquid, and it is same as the loss in weight when the object is taken inside the liquid, okay. Now see the relative density of the liquid, the relative density for the liquid is equal to the weight of the liquid displaced, which is same as the weight of the water displaced. So here you can see this fraction, weight of the liquid displaced divided by weight of the water displaced. Okay, because those are in same volume and those are same as the volume of the solid that is taken. Whenever the solid is taken in liquid, same volume of liquid is displaced as the solid is taken in water. Okay, so in water, whenever the solid is taken in water, it will displace the volume of water, and this volume is equal to the volume of liquid displaced when the solid is taken in the liquid, in this given liquid. Okay, so simply I am saying that this weight of the liquid displaced is same as volume as the weight of the water displaced. Okay, so that means the relative density of the liquid is equal to weight of liquid divided by weight of water of same volume, and those are of same volume, those are of same volume. Okay now, and from the previous line, see the see here, W1 minus W3 is the weight of the liquid displaced, so we can write W1 minus W3, and here we have W1 minus W2. So this W1 minus W2 is the here in the last line you can see W1 minus W2 is the upthrust by the liquid. Okay, that means the weight of the water, it is the upthrust by water, that means the weight of the water that is displaced, which is same as the volume of the object, the solid. Okay, so here this one is the final formula of the relative density. We have W1, we have W2, and we have W3. So we put the values, we can substitute those values, and we can easily calculate the relative density of the liquid. Okay, here the line you can see same volume of water and liquid displaced by the solid. So that's why the volume that displaced, okay, for the water and for the liquid is same. Whatever the water is displaced is same in volume as the liquid displaced. Okay, so this completes the chapter. Thank you class, have a nice day.